Thank you. So it's a pleasure to be here, and let's talk about optimal control a bit this afternoon. So this is a joint work with several colleagues, including Olivier and Joseph, who are just here, Pierre Martinon also from INRIA, and some colleagues from INRIA Sofia in southeast France. So what this talk is about is essentially non-linear optimal control. And non-linear is important in this case since we really want to treat general optimal control problems. So just for the record, this kind of problem is, for instance, here you see a so-called Lagrange cost with a Meyer part, which depends on the initial and final value of the state, x at t0, the initial term, and then the final term, x of tf, plus some Lagrange cost, an integral cost, with some functional scalar, functional f0 here. And of course, you have some dynamical constraints given by some function f, which of course depends on x and u at any time between 0 and tf. So, and you might add some constraints clearly on the control values and on the state, plus clearly some initial and final constraints, typically an initial value, which is known for the state. Our core interests are more or less twofold. We work on numerical stuff, okay, so essentially methods, a long time ago in Fortran, C++, MATLAB, Python, and so. Now in Julia, we're a bit newcomers in the field. But anyway, we're very glad that Julia has so many things ready out of the box. And also, rather for the math side, geometrical in the sense of differential geometric tools. And it's very easy also to do this kind of thing in Julia, which is very nice since you can really mix symbolic and efficient numerical tools in the language. So that's what we really like about this. I will try to give a few hints. Where do we come from? Essentially, at the first step of this story, we would try to bridge two things. The so-called direct methods. For instance, we, with colleagues, developed BOCUP, which is a solver that essentially use, I would say, collocation scheme, right? And with a C++ code, AD built inside using CPP-AD and so on. And with this, we try to bridge this kind of computation with indirect method shooting, okay? Say multiple shooting. And in this case, you really want to do things in a Hamiltonian fashion, because when you use the Montarguin maximum principle, for those who know what this is, which is the necessary condition for a control problem, you end up with a Hamiltonian differential equation that you want to solve. In this package, which was originally written in Fortran and MATLAB, there was a connection between shooting and path following methods, which is an efficient way to solve shooting. Okay, shooting generally is difficult because you do not know how to initialize it. Okay, so what you do, for instance, is you do path following, or what you can do is you bridge the two things. That is, you use first a direct code to have a rough initial guess, and then you switch to a shooting method. Okay, and this is more or less what I'm going to tell you about in this case. And this is what we did first using Python. Okay, we started this Julia stuff like 6 months ago, and you have still some material which is available online, application in a quite large variety of fields. So control is everywhere. That's quite clear. For instance, you will find here some notebooks in agronomics, biology, clearly standard examples. Godard, I will come back on Godard. We had a nice example this morning by Eduardo with Interesso who talked of Godard. We are going to come back to Godard. That's Olivier that will let you know a bit about this. Shooting, homotopy. Homotopy is the same one as differential continuation in this case. Direct and indirect methods, also some application to Riemannian geometry and so on. Space mechanics, that was a large trend for us since more than 20 years, I would say, and so on. So this was essentially done in Python, okay, to bridge this direct and indirect code. Now we are going to do this in Julia. So let me just give you the flavor of what we did. First of all, with a very basic example, okay? This is the very standard double integrator, okay? You have a dynamics of order 2, a scalar control in the state, which is a two-dimensional state in this case, and you want to minimize quadratic cost, essentially the so-called in energy cost, where you have this integral of the square of the control U. You fix some initial and terminal condition, okay, and the control is free, namely there are no control or state constraints in this case. So it's a very simple thing, you will get a smooth solution and everything. Okay, so what we do in just a few lines, this is the first version, sorry, the first version of the code of this description of this problem here. You just say that you define a model, okay, and in a very simple way, you will say that you have a time entry 0, 1, a state of dimension 2, one-dimensional control here, and you have some initial and final condition done, okay, and you solve. Of course, you precise the dynamics here, which is thus that x1 dot is x2 and x2 dot is u, and you have this cost, a Lagrange cost, okay, which means that you only have the integral part, and you solve and plot, okay. This is done using IPOpt. So thanks to our friends of AD-NLP models, we are able to use IPOpt in a quite efficient fashion in this case. You solve and plot, okay, and you get this solution where you clearly see that you reach the target that you wanted in terms of x1 and x2, okay, you reach 0 in both cases, right? The second way to do this, okay, is what we build using a very small DSL for our things. We wanted things to be as close as possible to the mathematics that you would write in this case. So what we just did is use a very nice package which is a ML style, okay, which allows you to write in a very simple way DSL. Okay, so in this case, what you want to say is that, okay, in the same way, we have a time, we have a state, we have a control, okay. You just here give the dimensions, initial and final value, some constraints here, very simple ones, okay, so it's x of 0, so it means that you have a boundary constraint at initial time, same at final time. Dynamics here, it's x dot, so it's a dynamics. You give it here, okay, you have a cost, again, the same cost, the Lagrange one, and you solve, right? And again, you get the same plot, right? This was a basic example, just direct code, okay? Now, let me give the floor to my colleague that will tell you a bit more about a more difficult example, the Godard case, where you will see that we can join, we can use the direct code to initialize the indirect, the shooting code, okay?
So, thank you, Jean-Baptiste. So, in this example, we will combine direct and indirect method. Donc, the Godard problem is well known, and the idea is to maximize the altitude of a rocket in a vertical ascent here. So you have here the objective function. And it's a problem with three state variables. So altitude, R, velocity, V, and you can see here all the forces, so the thrust, the drag, and the gravity. And you have the mass, and the dynamics of the mass is related to your thrust. So here we have normalized the control, so it's between 0 and 1, and we have a state constraint on the velocity. Okay, we do not want to. We have a maximal velocity. Okay. One more thing is that in this problem, the final time is free, as stated here. Okay, so it's an unknown of the problem. It's a decision variable. So first, we do the same things as before. We define the problem, and we will solve it by a direct method. So here you can see the parameters. Initial time is 0. Initial altitude is 1, so this means we start from the ground. It's the ground of the Earth. We start with 0 velocity, with normalized mass. Initial mass, it's normalized to 1. We have a maximal velocity, which is 0.1. And here you have the definition of the problem. So what is different compared to the basic example is that here, since TF is free, you have to tell that TF is a variable. Okay, you have the time, the state, the control, you can label the components of the state or the control and use them to define the constraints like this. So you have here the initial constraint, the final constraint on the mass. You have the inequality constraint on the control between 0 and 1. This one, I don't really know if it's necessary to ensure that the altitude is more than the initial altitude, since we want to maximize the altitude. And we have the state constraints on the velocity here, okay, the dynamics, and the criterion, which here is a Meyer criterion and not a Lagrange one. So the dynamics is given with a pure Julia code here. And you can note that the control appears linearly into the dynamics. And so we will have some singular arcs and some also constrained arcs into the solution. So now we can solve it by a direct method. Huh? Okay, with a grid size, a small one, a small grid size. Okay, so there are some few steps, and then you can plot the solution here. Okay, so altitude from 1 to the final altitude. We can see the velocity here. We can already see that there is a constraint arc here. Okay, this was the maximal velocity. You have on the left the state variable and on the right the co-state variable that will be useful to initialize the indirect method later. And here you have the control. With the control, we can see that there are 4 phases. A first phase with a bound control. The control is 1. A second phase with a singular control. A third phase, which we will see that is linked to the constraint arc. Okay, it will be a constraint. We can call it a constraint control. It's the control that makes you stay on the constraint. Okay, and then you have a off control, 0 control. Okay. So this is the end of the direct method, and now we want to use this solution to initialize and solve it with an indirect method to get a more accurate solution, to get a good, accurate solution about the switching times. So the switching times between these phases, okay? And you can notice also that, but this is quite classical in the direct method, that the control is oscillating, okay, on the singular arcs. But this is quite classical, and we will see that with the indirect method, we don't have this kind of phenomena. So to define the indirect method and the indirect shooting function, we need first to determine the structure of the solution, that is the sequence of arcs, so the bound and singular, constraint, and off arc. Here, it's just a plot of, I don't enter into the details of this, maybe I will see. Okay, see. Here, what do we do? We get the solution from the direct solution, so time, state, control, co-state. We define H1, which is the lift of the F1 was the control dynamics, okay? And H1 will be used to define what we call the switching function. And the switching function, when it's 0, it tells you that you are on a singular arc or here on a constraint arc. We define also here the constraint, the state constraint, okay? And we will plot everything to determine the structure. So on top, you have the control. In the middle, you have the switching function, and you can see that it is 0 on the singular part. And then on the constraint arc is visible here with the last plot of the state constraint, okay? So now we have the structure, and we can define the shooting function, which is more or less a concatenation of these 4 phases. But what is needed to define the shooting function? We want to integrate these four phases. So we need to have some function to compute the flow associated to this control, the flow associated to this control, singular control, the flow associated to the state constraint control, and the flow associated to the off control. So we have to define these four flows, and then we will be able to define the shooting function. To define these flows, we need, what do we need? We need the control laws in feedback form. We need 4 control laws in feedback form. So here we have some details, some mathematical details to compute the control laws in feedback form. I won't detail a lot this part, but what you can see is that US is the control law is a singular control in feedback form, and it is given by some computation of Poisson bracket of order 3, of length 3. Okay. I don't give some details about that, not so much, but you have also here the control, the constraint control, okay, and you can see that it is given by some Lie derivatives of F0, which was the drift, and F1, which was the control field. And because you have a state constraint of here of order 1, but you have a state constraint, you have a multiplier associated to this constraint, and the multiplier also can be computed in feedback form, and here you have the expression. Okay, so this is the mathematical part, and this will help us to define everything with Julia, and this is done here. So it's quite similar, as you can see. H01, 001, H101 are simply Poisson brackets and are computed like this. So it's just a syntax to compute Poisson brackets. And you have the singular control, which is minus H001 over H101. Okay, so this is for the singular control. You have for the constraint control, and then you can define all the flows by command that you have in a method that you have in optimal control. And what you can see is that just with the OCP that we have defined before and a new information, which is a control in feedback form, we have a flow. So now we have everything to define the shooting function, which is barely the concatenation of these flows. So here is the shooting function. As you can see, here we have in the unknown of the shooting function, the initial co-state and the 3 switching times and the final time. You can see that we just concatenate the flow. So we start with F1, it's when U is 1, Fs, Us, singular control, boundary control, 0 control, and then we just define the equation to solve. So here we have the constraint on the final mass. We have some transversality condition because the final altitude and the final velocity are free. Okay, we have some condition which tells you that you enter into a singular arc, and some condition which tells you that you are entering the state constraint arc. Okay, and at the end you have this condition which comes from the fact that TF is free. Okay, now what we have done, we have the structure, we have determined the structure, we have defined our shooting function. We have to find now a 0 of this shooting function, that's it. And to get a 0 of the shooting function, we will use a Newton solver. So it's quite sensitive to the initial guess. So we need a good initial guess, and this is the last part before the resolution. So here we have a simple trick. It's not very clever. It's just a simple thing to get a good initial guess from the direct method. T, X, everything was given by the direct method. For instance, P0, it's just P at time 0, okay? And to get the switching times, it's a simple thing. So we can see that we have everything. We can see that it's not very accurate since here you have the norm of the shooting function, which should be 0, or at least close to 0 at the end, but here it's not close to 0. So let's go to solve this, and let's see what happened. So to solve it, it's very simple. We use here minpack, but we could use another package to solve a nonlinear equation. So we simply solve it with minpack by calling fsolve on our shooting function with our initial guess. Okay, and then we have everything: the go state, the switching times, and the final time. And now the shooting function, the norm of the shooting function is quite reduced. So it converges. Okay. What we do at the end is just we plot the new solution and compare to the solution we got from the direct method. Okay. But the difference here, when we solved the problem with the direct method, we started with an optimal control problem and we had a solution of an optimal control problem. But with the indirect method, you have some unknowns which are go state, times, and such like that. And you don't have an optimal control problem. And at the end, your solution is not the same. So we have to recover something analog to the optimal control solution. And to do so, it's quite simple. We just have to use the flow we have defined before and compute the solution thanks to the 4 flows we have defined before. To do this in just one line here, we have defined an operator with the with the multiplier sign, which concatenates all the flows, and you tell when you have to switch between them. Then you call it. It's a classical flow. You get the solution and you can plot it, and then you have the solution here. You have the indirect solution on the direct solution, and just take a look at the control. You can see that everything is more accurate. Okay, so this was the part, the combination of direct and indirect method, and I just sum up what we have presented here. As you have seen, we have a high-level modeling of optimal control problem. We have an abstract form and a functional form. We have an efficient solver, since at the end it's solved by hyperop solver, and it's handling sparsity, automatic differentiation, and so on. And we have also implemented some examples where you have the problems and the solutions. And I just leave the floor to Jean-Baptiste for the end.
Actually, so the message is quite clear. Direct is good, indirect is good. When you put them both all together, is better. Okay. Just a few words about what we are going to do. You can see here a quick video where we use a REPL maker to make a REPL, in fact, to define in an abstract fashion our problem. So maybe we can see here, okay, line after line, that we enter the problem in this DSL form. This is a minimum time problem, double integrator again, but mean time, okay, and you just expect a solution to be bang bang one, okay, so a simple one. So using this REPL, you just enter line after line, okay, your problem in abstract form. Again, when you see this QT, means that for every time t, okay, that you have this constraint on the state and so on, and this is the result where you clearly see this bang bang form here. All this, okay, is on the website, so you can have a look at it. Just to conclude, what we are going to do is to add more solvers, that direct shooting, for instance, collocation, etc. Path following, of course, and we are open to contributions and, in fact, ideas, of course. There are already some problems online, so you can have a look at this list of problems, quite a lot of them, with different features. For instance, you can see here the double integrator, which is a bit more complicated than the simple one, because you have this L1 norm of the control here, okay, so you expect this kind of bang-bang solution here, bang +1, bang -1 or +4, -4, plus a singular part here, etc. Okay, so this is all available online, and you can use it for testing. The website is controltoolbox.org, okay, so here you will find the documentation on the root package, which is optimalcontrol.gl, okay, and of course, let me give some credits to a lot of people, including people in the room, and in particular, we're very glad to use AD-NLP by Tanguy, who just said a few words at 2 p.m. And of course, we heavily use ML-style to pass the small DSL that we made. Thanks for your attention.
Yeah. Okay. Yeah. So first question is, you had this example that was showing the direct and indirect method. You showed that they compute about the same result, right? But the indirect method had a timing output from IP-opt. The direct method did not have a timing method with it. I was wondering if you had a comparison of the timings of anything on any problems there.
Yeah. Well, actually, we did a comparison with a jump. Okay. If you hardcode the problem in jump, it's still quite faster. There's a ratio, I would say, 1 to 10, okay? But actually, Tanguy did a tremendous job more or less last week. And with now some sparse session stuff, it scales quite well. And I mean, in the end, it's all IP-opt solving. So it should be fine in both cases, I would say, right? But we didn't want to hardcode stuff. We really want to have a description as close to the math as is possible. So that's why.
But the direct method's not using IP-opt, right?
It is.
Oh, it is. Okay.
It is. Yeah.
Oh, it's just not showing the full printout there.
Well,
I was looking at the docs here.
No. Yes, it's IP-opt. In fact, because in the case of AD-NLP models, we switch to IP-opt as a solver, right?
Okay.
Yeah.
Yeah, because I thought it said it was using MinPack as a solver here.
No, that's for the shooting, okay? Because when you shoot, you look for a 0.
Yeah.
That's when you go for a solve.
Yeah,
okay?
So I was wondering if you had a timing of that as well, because that's the only one in there that didn't have a timing in the printout.
Oh, the timing you mean for the shooting, right?
Yeah.
Yeah, well, that's absolutely fast. That's a question of seconds on a standard laptop.
Okay.
Yeah. Why? Because you have the direct code and a very nice guess.
Mm-hmm.
When you start. Otherwise, you just get lost.
Mm-hmm.
Okay. You have 4 arcs, even in the Godard case. So it's a classic case, okay, but it's not that easy, in fact, because you have bang, singular, binary arc, bang again. So if you do not, in some way, capture the structure of the control at first, you just lost.
Yeah. And then the other thing is, so you have this DSL here, but a lot of the DSLs that we have within the Julia ecosystem are built on top of Modeling Toolkit. I was wondering if, since there's a separate dynamics specification here, if they can interrupt well.
They can sure interact. That would be nice to do so. The difference is that we really wanted stuff just so close to the way we write mathematics, okay, including the differential geometric part. Yeah. So that's why. But of course, it would be nice to have a bridge between the two things. That's what clear.
Yeah. So yeah, I guess, yeah, we could talk about building a bridge.
Yeah, sure. Yeah.
Hey, thank you so much.
Thanks.
So like kind of 2 related questions. One is in the direct method. Can you guys do general nonlinear constraints on the, on the states and everything?
That's the basic start that we wanted, full nonlinear stuff. Okay.
Cool.
Yeah.
And then, so I guess why then was in the problem you were doing some like switching methods to like enforce the constraints? The R max, I think it was, the R min. I'm kind of remembering.
Are you talking direct method or?
Yeah, in the direct method.
Yeah, okay. I mean, in the direct case, for instance, maybe I can go back here just to give you an idea. Okay. For instance, if you look at the Godard case, okay, what I can tell you probably is this. If you look at the GSL version of the problem, okay, there is only one difference, which is here. You see that everything, in fact, is linear. That's just a box thing. So this we do take into account because for IP-opt it's nicer. right?
Yeah.
Suppose that you put some non-linear expression of u here, so we'll switch to non-linear stuff
Okay. Yeah,
automatically.
gotcha.
Yeah, that's the parser that does this.
Where was I seeing the G function? Was that in the shooting method case then?
What do you call G? Oh, G. Yes, G. I mean G. That was for the indirect, for the shooting. Okay, because you want to compute. Yeah,
that was for the shooting. Okay.
yeah. Look. This one here, right? That's the constraint. You use it because you want to compute some Lie derivative to compute the boundary control.
Got it.
Yeah. Eduardo.
Hi, thank you for
Hi,
the
yeah.
talk.
Thanks.
I was wondering, so for the direct method, it seems pretty plug and play, so an expert wouldn't
That's the idea. Yeah.
necessary. Could it be possible to automate part of the indirect method modeling part?
Well, that's more or less what we do here. See, for instance, you can label equation. Okay, you have a label here. Okay, for instance, for the final value of the mass. Okay, you might have noticed that, for instance, m is equal to x3, so automatically you have aliases. You could put x bracket 3. Okay, but you have this aliases for the state components here, and you see that you have this label one here. For instance, when you define the shooting function, you see here that we refer to this equation, meaning that here, okay, constraint, you call from OCP the constraint number 1, okay, to retrieve, in fact, the value of the mass. So there's an interplay between, of course, the definition and the stuff that you use for the indirect code, sure. And again, when you compute the flow here, it's straight away from the OCP. Okay, so you will use again the dynamics here to build the flow. Okay, yeah, sure.
Yeah, I guess we can take further questions offline, but just thank the speaker again.
Thank you.